Hey there, in this video we're going to cover chapter 7, well section 7.1. We're starting chapter 7, and so we're going to talk about confidence intervals. In this section we're going to present methods for using a sample proportion, so in section 7.1, to make an inference about the value of the corresponding population proportion. So first of all, the population proportion is the probability of successes in a single trial of a binomial experiment, and we denote the population proportion P. Sometimes you might see it as pi. So the sample proportion then P hat is the best point estimate of the population proportion. So this is P hat, or sample proportion, is the best way to approximate the population value. This point estimate is an unbiased estimator, and it is also the most consistent value that estimates the population proportion. So let's look at our example. Let's revisit the M&M colors example from before. So are the claimed percentages of M&M colors reasonable? The statement from the M&M company says that their color blends were selected by conducting consumer preference tests, which indicated the assortment of colors that pleased the greatest number of people, and then they created the most attractive overall effect. So then each large production batch is blended to those ratios and mixed thoroughly. However, since the individual packages are filled by weight on high-speed equipment and not by count, it is possible to have different amounts, different color distribution per bag. But what they claim, the company claims that in the regular bag of M&M's chocolate candies, you're going to have 24% blue candies, 20% orange, 16% green, 14% yellow, 13% red, and 13% brown. So let's go through, and I've identified the different steps of this study. So first of all, what are the observational units in this example? And so here what we can say is that the observational units are the candies in a regular bag of M&Ms. What is the variable being recorded? The variable being recorded will be the color of the candy chosen. So if you pick a candy at random, what's the color that you get? Are the percentages for each color given above a statistic or a parameter? So what do we think? So 24%, 20%, so those are the percentages, and the different proportions for each color. Are they a statistic or a parameter? We will say that this is a parameter, and the reason being is that these are the percentages claimed by the company. So we can say these are the values claimed by the company. State the appropriate null and alternative hypotheses for the color blue. So we're going to focus on right now just the color blue. We'll do this one together, and then you guys can do the other colors on your own. So both in words and in terms of in words and in symbols, in terms of the parameter for testing the conjecture that the percent of a blue M&Ms in the bag of milk chocolate candies is 24%. So in words, what will we say then that the null hypothesis is? In the past, I have talked about how the null hypothesis is the by chance model. And in this case, we're not really doing anything by chance, so it's a little bit different. So another way to identify the null hypothesis is that the null hypothesis is the claim. And so in this case, the null hypothesis will be the claim that the company is making. So the proportion of M&Ms, of blue M&Ms, in a regular bag of candies is 24%. And I guess I won't say 24%, we will say 0.24, because we're talking about the proportion, right? Not the percent. And how do we say that in symbols? In symbols, we're going to say the proportion of blue M&Ms. So we want to use, the null hypothesis always refers to the population. So we're going to say P equals 0.24. The alternative hypothesis is that the proportion of blue M&Ms in a regular bag is not 0.24. Right, so essentially if the null hypothesis is the claim, let me write that in here. So the null hypothesis is the claim. Then the alternative hypothesis is, well, the alternative rate, not the claim. So the proportion of blue M&Ms in a regular bag is not 0.24. And sometimes we may see this differently. We may see like it's greater than 0.24 or it's less than 0.24. But in this case, we're just being told that we can't really make an assumption of whether it's greater than or less than, because we would need more information to make that decision. So it's either 0.24 or it's not. So that's the alternative hypothesis. So in symbols, we're going to say P is not 0.24. All right, so now this is dealing with the population. We have our null hypothesis or our alternative hypothesis. So now, using your sample from when we did this activity back in week 2, so you will look at your sections 2.1 and 2.2 from this class, find p hat for each color. Now if you want to do it again, then that's fine. Just do your simulator and it will give you a brand new bag of M&Ms, so count each color. And so for me, I did my bag of M&Ms, and so here is the simulator. So it gave me 53 candies, right? The average is 56 candies in a bag of M&M. That's what we discussed back in that activity in section 2.1 and 2.2, that the average number of candies in a regular bag of milk M&Ms is 56. Now when I did this simulator, it gave me 53, which, you know, not too far off from 56. And then I counted the different colors, the blue, orange, green, yellow, red, and brown. So let's go back to our notes. And so I counted 14 blues, but here I want the sample proportion. So I'm not going to write 14, I'm going to write the proportion. So what did I say? 53 total candies. So let's write that in. So with 53 total candies in my bag of M&M, so you do it for your own and see what your percentages are. So my blue candies were 14 out of 53. My orange candies, I had 12. For green candies, I got 5. Yellow, I had 10 out of 53, all of these. And then 5 and 7. So if I add all of these, I should get 53 out of 53, which is then 1, right? All of these proportions should add up to 1. And let's find the decimal as well. So 14 out of 53, I got 0.264. And then 12 out of 53, I got 0.226. And so on. So we can put all these other ones just in case, as we want to later find the confidence intervals for these. So 5 out of 53, I got 0.094 again, and then 7 out of 53, 0.132. Now these should be really close to 1. Here, again, we are approximating, right? I'm taking it to 3 decimal places, so my approximation will be off. When I added all of these up, I got 0.999. So it should be 1 or very, very close to 1 because of rounding, we're a little bit off here. All right, so we have our proportion, and here we're gonna, as we said, we're gonna focus on the blue M&M. So 14 out of 53 and 0.264 is our proportion as a decimal. So now we're gonna go to try to find the confidence interval. So what is a confidence interval? Confidence interval or interval estimate is a range of values used to estimate the true value of a population parameter. So a confidence interval is sometimes abbreviated as just CI, but what a confidence interval is really doing is it takes our sample proportion and tries to then do statistical analysis and calculate an error to say our population parameter should be between this and this value, between two values. And then what we're going to see is we're going to try to find a confidence interval based on our sample, right, on our 14 out of 53, and then see where we are compared to the population, compared to the claim from the M&M factory. So notice that our sample is 0.264, which as a percent, what is that? That will be 26.4%. The claim from the M&M factory is that there are 24% blue M&M candies in a bag. Our bag had, or my bag had 26%. So not too far off from the claim. All right, steps for finding the confidence interval is finding the point estimate. So we found our population point estimate, which is p hat, which is the proportion of blue candies, the 14 out of 53. Now we're going to verify that the sampling distribution can be approximated by the normal distribution. So this is what we did last time in section 6.6. So this means verify that n times p hat is more than 5 and n times q hat is more than 5, which really just means the number of successes is more than 5 and the number of failures is more than 5. In step 3, find the critical value z alpha over 2 that corresponds to the given confidence level. And I'll talk about what that means. And then find the margin of error. So I'm just kind of listing the steps here, but then we're going to go in and dissect what everything means. So find the margin of error. And then once we have the margin of error, so that's the big part of finding the confidence interval, then we can put the confidence interval together by finding the value of p hat minus the margin of error and p hat plus the margin of error. So our sample proportion, so our 26.4% minus the margin of error, and then our 14 out of 53, or p hat, plus the margin of error. So then your confidence interval will look like p hat minus e, and p, remember, so p hat is our sample proportion, and p is the parameter. So we're saying the parameter is between those two values. So that's what we're looking for. Now, what is a critical value? Z alpha over 2. So a critical value is the number on the borderline separating sample statistics that are significantly high or significantly low from those that are not significant. So we've been calling those more than 2 standard deviations away, right? So we want to find, so essentially here, alpha over 2, we have your z-score. Z equals 0 is right in the middle. And then you have z alpha over 2. So essentially a z-score that then gives you the area to the right, and then the other half of it is the area to the left. So let's find a critical value corresponding to 95%. So to find it for the 95% area, so that means that we're going to have in between here, so if we look at this picture, so you're going to have 95% of the area is in there. So then that means that on the tails, right, in this tail you have the whole thing is 1. So then in the two tails you're going to have 1 minus 0.95. Convert to 95% is 0.95. So that means that in this shaded area, in red over here, not the yellow, I guess it's green, I shouldn't need to shade it again, but in there you have 1 minus 0.95, which is 0.05. But then there's 2 of those. So to get just one of them, then we're going to need to take half of it. So half of it, that's why we are dividing by 2, because you have the 2 greens and we only want one of them. So then this is the 0.05 divided by 2, which then gives us alpha over 2 is 0.25. Now we're going to look at this. Now this represents an area. So we're going to look it up in our Z table of Z-scores, but we're going to do it backwards. So in previous sections, we've had the Z-score, and then we look at the area. Now we have the area, and we want to look up the Z-score. So let's bring in the Z-score table here. And so I have, because my area is so small, 0.025, so I'm looking over here for 0.025, right? I have the area, not the z-score. So 0.02, here we go. So 0.0250. So that's this entry right here. And so let me highlight it. So this is the area that we're looking for. So what's the z-score that goes with that? Negative 1.96. So let's go back to our notes. So that means that the value, the z-score, this value right here is negative 1.96. The nice thing about being the bell-shaped curve and that everything is symmetric is that then I know that this z-score here is going to be 1.96. And so then my z alpha over 2 is 1.96. So that's the positive one. We can use either one, so negative 1.96 or 1.96. Oftentimes we're going to be looking at the positive one, but I find it easier to do the negative because then I'm looking at that area, right? The one, since the table gives me the area to the left, I pick this one because this already gives me the area to the left. If I wanted to find this one using the table, then I have to do the 95%, right, the area in yellow, plus that 0.25. So just for practice, we can do that. So let me do the same shape again. So essentially what I'm saying is that if I wanted to find this z alpha over 2, then I have to find that value. But the table always gives us the area to the left, so that means I'm going to include the entire 95% here plus that 0.025. So that means that the area to the left is how much? Is the 95% plus that other stuff. So 0.95, right? 95% as a decimal plus the 0.025. So what am I going to be looking at? So then the area to the left was going to be 0.975, right? 0.9, essentially the 5 plus the 25, so 0.975. And so when I go to my table, back to the z-score table, I can see that the negative z-scores end at 0.5. So I need to go to my positive z-scores. So I'm going to go to the positive z-scores and then find 0.975. So again, I'm looking at the areas here. So 0.97, you're probably faster than me, 0.975 right there. And so that's the one that I want to find the z-score. So that is 1.9 and 6, right? So same thing, but positive. So then I know, okay, so then this is 1.96. But, right, so that's my z's alpha over 2. This just, finding the positive one makes me add in this whole other area in yellow, whereas the going for the smaller one, the negative z-score, I know that then this is negative 1.96, and because of the symmetry of the bell curve, then the other one is going to be the positive of it. So you can do it either way. I find it easier to find the negative one because that already gives me that area to the left, so I don't have to do any extra math like adding that 95%, that 0.95, and then figuring out that area. So I find it a little easier to just find the negative z-score and then just take the absolute value to give the positive. Z alpha over 2 then is 1.96. Now back to our M&M example. So we want to construct a 95% confidence interval for the proportion of blue candies. The hypothesized parameter given by the M&M company is that the proportion of blue candies is 0.24. P equals 0.24. And is this value contained in our confidence interval? So let's first construct the confidence interval and then we'll see if our value is contained in there. Recall your sample data. The proportion of blue M&Ms from your sample, p hat was, so in my sample, it was 0.264. And now verify that n times p hat is more than 5 and that n times q hat is also more than 5. So p hat is our proportion, which is the 0.264, and q hat is 1 minus p hat, right? So what do we know? We know that from my bag, n was 53 candies. I know that p hat is 0.264. And so q, and I put a hat in it because we're talking about a sample, is 1 minus 0.264. And so verifying NP hat. So we're going to do the 53 times the 0.264, which I end up getting 13.99, which I'm going to round to 14, which notice that was my number of blue M&Ms. So that's why earlier I said it's really when you do NP greater than 5 and Q hat greater than 5, you're really checking that you have more than 5 successes and more than 5 failures. So for the blue candies, I had 14 blue candies, so that's more than 5. And so N Q hat should really then be close to the 53 minus 14, which should be 39. But if we do the 53 times 1 minus 0.264, we should get 0.39 and change, which we can round to just 39. Or 39 and change, so we can round to 39. So that adds up to 53. Are they more than 5? Yes, that is definitely greater than 5, and that is definitely greater than 5. So it meets the criteria for approximating this binomial distribution with a normal distribution. Now part 3 is find the critical value for a 95% confidence level. This is the critical value that we found above. Right, so then I'm going to go back here. I would technically have to do the same thing. So if instead I had asked for a 90% confidence level, then you will go through this process. 90% is 0.90, 1 minus 0.90 is 0.1, then alpha over 2 will be 0.05, and then you go find the areas. But here we already did it, so I know that my critical value will be the z's of alpha over 2, which is 1.96. So let's put that in here. So we have our critical value. Z alpha over 2 is 1.96. Now we need to find the margin of error. So let's find the margin of error. Now remember that the margin of error, we had written the formula up above. I'm just going to copy and paste it over here. So the margin of error is this formula, or critical value times the square root of p hat, q hat, and then over n. All right, so in part 3 we found the margin of errors, the critical value. So then to find the margin of error, I need my critical value. So this is the critical value. And so I'm going to have 1.96 times then the square root of p hat, q hat. So p hat is 0.264. Q hat was 1 minus 0.264, which is 0.736, and then divided by n. My n was 53, the number of candies in my bag. And so this is going to be 1.96 times the square root of this stuff. So let's do the numerator, and then we'll divide by 53. When I do 0.264 times 0.736, I get 0.1943. So I'm going to round to, well, let's leave it 0.3 to 4 decimal places. Then divide by 53, take the square root. So my margin of error so far is looking like 1.96 times, and let's do 4 decimal places on that. And I got 0.0605, rounding to 4 decimal places. Pay attention in the homework how many decimal places you want to round. Usually the more the better while you're still doing the calculations. And now let's do, then the margin of error is that times 1.96. So still rounding to 4 decimal places, I get 0.11858. So to 4 decimal places, I'm going to round that 5 to a 6. So that's what I get for my margin of error. So now I'm ready to build the confidence interval. With the margin of error, now we can say p hat minus e and p hat plus e, and that gives us the endpoint of our confidence interval. So I'm going to do p hat. Now remember, p hat is our 0.264. Well, that was mine for my blue candies. So then I'm going to do p hat minus the margin of error. Then it's going to be 0.264 minus the 0.1186, and then p hat plus the margin of error is going to be the 0.264 plus 0.1186. And let's see what those values are. Let's put them on our calculators. For the lower endpoint, I get the 0.264 minus 0.1186. I got 0.1454, rounding to 4 decimal places. And then for the bottom one, I got 0.3826. So that means that our 95% confidence interval for blue, for the proportion of blue M&M candies, is, we will say, the lower endpoint, so 0.1454 is less than our population proportion, less than 0.3826. So what this says is really that with 95% confidence, we can say significance level that the population proportion is going to be, so the true proportion of blue M&M candies is somewhere between 0.1454 and 0.3826. Now, what was the claim by the company? The company claims that the proportion of M&M, of blue M&M candies in the bag is 24%, so 0.24. Is that included in this confidence interval? Yes, right. 0.24 is P equals 0.24, which is the company claim, is included in our confidence interval, in our 95% confidence interval. So it could very well be that that is the proportion. So what we just found is that, yeah, the company could be right? So they are, with 95% significance level, we can say that the true proportion of blue M&M candies contained in a regular bag is between, what would you say, that 15% and 38%. So 24% is very plausible. So the company claim is correct, very likely to be correct. So that's what essentially a confidence interval is telling us. So I encourage you to do on your own, maybe do the ones for orange and green and see, is the claim correct? So I will be interested for green, for example, because my data for green is, going back up, oops, I'm in the wrong file, just one second. Where is my notes? So back over here, my green was 5 out of 53, so 0.094 or 9%. And the claim by the company is that there's 16% green M&Ms, right? So then maybe my sample proportion is not a very good estimate, but a sample proportion is supposed to be an unbiased estimator. And so check what is your proportion of green candies. So I'll be interested to see based on, right, and as we each construct different confidence intervals, we can start to see. And so that's one of the things that I may ask you to, in a survey, to put in, what was your confidence interval for green M&Ms? And then we can see, based on everyone's confidence intervals, is 16% in there? I have, well, I guess 9% is not too terribly far from 16, but I'll be curious to see what the confidence interval for green M&M candies will be. So try that on your own. It will be good practice to work with the confidence interval. And so this, we did it for a 95% confidence. So if I change the confidence level, right? So if I did 90%, everything will stay the same in terms of the how you do it, where you find your p hat, you find your number of successes has to be more than 5, your number of failures has to be more than 5. The margin of error is your critical value times the square root of p hat q hat over n. So the thing that will change will be your critical value. When you have 90%, this will be then 0.90, and then it will be 1 minus 0.90, which is 0.10. And so your alpha over 2 will be 0.05. So that's what you are now going to be looking at in our table, right? So I'm going to go over here. I'm going to look for 0.05. So, which notice actually that that is highlighted there, is 0.05 lands right in between these two. So we take this value in the middle. So you average them out. So it will be 1.6, and what is that? 4, between 4 and 5, so 1.645. And so if I follow that arrow, it tells me that the z-score for an area 0.05 is negative 1.645. So that will be for a, so I will look at my critical value will be the positive one, though. So it will be positive 1.645. And so that will be the one that I would use for a confidence interval of 90%. And then we can change the confidence. I would say, what about 60%? But the higher the confidence, the interval is going to change. So one of my questions is, how does the interval change? And in section 7.2, we'll talk about that. All right, contact me if you have any questions.